Problem number 13. A ballerina with a moment of inertia I is quickly twirling with angular velocity omega. In her hand she has a pen of mass m at a radius r from her axis of rotation. The ballerina releases the pen. Afterward, what happened to the vertical component of the angular momentum of the system consisting of the ballerina and the pen? You may ignore all friction, but not gravity or normal forces. Solution for problem number 13. There are no external vertical torques in this problem, as both the gravity and normal force are vertical, so the vertical component of angular momentum is conserved. That's answer C. It always stays the same, and that was solution for problem number 13. Problem number 14. Two blocks of mass m are placed on top of each other, and the bottom block is placed on the ground. The ground is frictionless. The static and kinetic coefficients of friction between the two blocks are μs and μk, with μs greater than μk. The blocks are at rest initially. When a constant horizontal force F is then applied to the bottom block, which of the following graphs could show its acceleration as a function of force F? Solution for problem number 14. For small forces, the blocks move together and the acceleration is linear in the force and equal to F over 2m, where slope is 1 over 2m. At a certain threshold, the top block begins to slip, because μk less than μs. The friction force decreases suddenly at this threshold, so the acceleration of the bottom block increases suddenly. For higher forces, the acceleration is again linear in the force, but with a greater slope. The equation for this acceleration is this one, and we can see that slope is twice greater than in the first case. If we check all 5 graphs, we can see that only graph B is the correct answer. That was solution for problem number 14. Problem number 15. As shown in the figure, a vessel contains 2 types of liquid. The liquid with density ρ1 on the top and ρ2 on the bottom. The depth of the top liquid is h1, and the interface area between the top and the bottom liquid is S1. The bottom liquid has a depth of H2. The area of the bottom of the vessel is S2. What is the gauge pressure? Other words, pressure in excess of atmospheric pressure at the bottom of the vessel. Solution for problem number 15. The gauge pressure is 0 by definition at the top, so it is ρ1 h1g at the liquid interface. The pressure then increases by ρ2 h2g from here to the bottom of the vessel, giving the answer this one. So it is answer A, and that was a solution for problem number 15. Problem number 16. Liquid droplets store a given amount of potential energy per unit surface area due to their surface tension. When 2 identical, nearly spherical liquid droplets coalesce on a certain type of surface, part of this energy can be converted into upward kinetic energy, causing the coalesced droplet to jump. Assuming the conversion is 100% efficient. How does the maximum height h depend on the radius r of the initial droplets? Solution for problem number 16. First, let's write equation for initial surface area. That will be for two droplets 8 pi r square, and the initial volume was 8 over 3 pi r cube, which is 4 over 3 pi big R cube, where big R is the final radius for final droplet. So from here this big R equal cubic root from 2 of small r, and area surface for new droplet equal to 4 to power 2/3 pi r square. Now let's count what is total mass and count what is change of area surface. So total potential energy will be rho multiplied by volume, which is 8 over 3 pi r cube multiplied by gh, and that must be equal to surface energy change, which is gamma delta S, which is this expression. And we see that finally we have h proportional to r power -1, which is answer D, and that was a solution for problem number 16.